Hopefully we're recording. I reviewed kind of the summary of what we've seen this summer. What I want to do, so on the webpage I've got some notes. I think they're under entanglement. There's a tab across the top. They're not under the same main page. I kind of put these off to the side. This one's called Epr and entanglement, and there's another one on Bell's theorem, so we'll see how far we get. So what I want to do is kind of talk a little bit about how you go from talking about one observable at a time to two observables at a time, and then we'll kind of just bootstrap that, just assume, well, you basically recycle that way of thinking to talk about two separate particles at the same time. And you'll have to just trust me that it works. You take official courses, you'll work through all the examples. You'll see why it's done this way. And then I want to talk about the Epr Incompleteness Argument, which is the argument by Einstein, Podolsky, and Rosen that quantum mechanics must be incomplete. So they didn't quibble. They weren't quibbling that it didn't give good answers. They were saying that it couldn't be a complete theory of nature. So I will present that in this video, and then in the next video try to go over Bell's theorem, which is an answer, or at least a kind of a more detailed analysis of this. All right. So multiple degrees of freedom. So we've talked about spin, we've talked about position, and even when we were doing work through the example that Einstein went through in his lecture notes of neutrons scattering off a crystal, we had a situation where we had both position and spin at the same time. And so at the time, as I'm kind of showing these things to you guys, I really came to appreciate almost the sly way that Einstein chose his examples to introduce things for later on. So he did things like introduce multi-particle states and extra degrees of freedom without even telling you. He just said, "Oh, here's how we're going to do it. It's just obvious." Well, is it really obvious? I don't know. All right. So let's imagine you have a particle with both spin and momentum. Well, what we saw is we just labeled them P and plus or minus Z. Let's just say choose plus Z for concreteness. We said, well, there's some, now the particle or system is described by this state, which is just a generalization of what we had before. No big deal. Well, okay, let's unpack this. What are we really doing a little bit? So what's really going on is, so first of all, to do this, what we're meaning to imply is that if you measure momentum, you would find P, and if you measure spin, you would find plus Z. And to be able to make this is one state right now that is equal or is correlated with definite results of two different attributes. So these attributes must be compatible somehow. If you try to do this with position and momentum, we know that you can't simultaneously be in an eigenstate of position and momentum. So you couldn't do this. So what's necessary is that this observable, referenced here, commutes with this observable. Okay, so that's a statement that has to be true. Okay, and these are separate then independent quantities. And what we're going to do when we write this kind of notation is we're basically saying, okay, this information kind of sits side by side. And if I measure momentum, it just does what you think it should do. And if I measure spin, it just does what you think it should do. And if I measure momentum and I don't care about spin, somehow that stuff the spin information just is irrelevant. If I measure spin, but I don't measure momentum, then the momentum information is irrelevant. So how are we going to do that? And we have to come up with some sort of rules for how to do that. And what we're going to assume then is the following: that this state, well, we have to go through what were the postulates. You needed linearity or superposition principle, inner product, all that. We're going to assume that we can just kind of recycle the 1 degree of freedom at a time information, and experiment verifies this or vindicates this assumption. So what would I mean by, let's say I tried to take the inner product of P, this is my state psi, and it needs to be a unit vector. So let's see what that would mean. P plus Z with P plus Z. And I don't want to get into details about the direct delta function and the fact that I don't want to get into too many technical details, but what we're going to assume is that this means simply that that the inner product of a state with 2 attributes just factors into the separate bits. So you just assume that means, oh, that's P with P, whatever that means. We'll say it's 1 times plus Z plus Z. Right? So what we're going to assume is that our way of writing states, the rules we're going to deduce to make all this hang together, is that if these are compatible observables, fine, then, and they're independent bits of information, and they have nothing to do with each other, and so when you take the inner products, we're going to need that basically it factors into the separate inner products. Just the piece of information factor. And this is what we're going to need to get the probabilities. We would want probabilities of completely independent things to factorize. The probability of heads, of me flipping a coin and getting heads, is completely independent of whether or not I'm wearing shoes. And so you just assume that the way you get that to work is that everything has to factorize. We're going to just guess that has to work out. What we're really guessing is that I'll just tell you what this means. What we're really saying is, in mathematician speak, I'm saying that this is just what you need to have to make things work out right. What we're really saying mathematically is that this kind of combined system lives in what's called a tensor product space. So the tensor product is a way of taking 2 vector spaces, gluing them together to get a bigger vector space, whose dimensionality is the product. So if I do, let's say, a 3-dimensional space, tensor product with a 2-dimensional space, the resulting dimensionality of the final space is 6, not 5. So a Cartesian product is, you would add the 2 dimensionalities. Tensor product, you multiply them, they're bigger. Tensor product spaces tend to be much bigger.
So I've never really been clear on the exact definition of a tensor in the first place. Is it just like a generalization of vectors and scalars? Or?
Yes. I can do that after. We don't need the language of it. For us, it's just language. What I just want to establish for you is, if you want to look it up, everything I'm saying here has a concrete. You don't have to be hand waving. It's a precise mathematical object that was well defined, has all these properties. Look them up, work them out. So in that language, the way a mathematician would want you to write this, if you're being precise, is you would say that the state lives in the tensor product space, and it would be, this is the symbol for tensor product, times with a circle. They would say this is actually what we mean by that. But you can see, since I'm fundamentally lazy, that's more time than this, so I won't write it that way. But there are times when it's necessary to really spell things out. I do go, even on my own stuff, I will go through and just really write it out so I'm clear on that. All right. Okay. So that's what a mathematician would say. I'm not going to dwell on that too much. I just wanted to write it down for you. So the key is, though, look at what's happening. The state has a bit momentum and a bit which is spin, but when you go to do the computations, they kind of pass through each other. They don't talk. If you have an interaction which mixes them, then what will happen is they will be intertwined, and the calculation won't factor. If everything completely factors into something with momentum or something with spin and never get intertwined together, then the whole calculation will always factor like that. And yeah. All right. Is that okay? I think that's all I need to say. But that's all I really wanted to get into that. Multi-particle states. Well, we're going to recycle. So when we have multi-particle states, we're going to recycle the same ideas. Okay? So we need, again, so when I had single particles with two attributes, but they were independent, we needed a mathematical construct which allowed them to kind of separate, and knowing momentum somehow didn't mess up the spin, knowing spin didn't mess up the, and it was that factorizing rule. Okay? Well, multi-particle states, there's stuff going on in Jupiter. We're all part of the universe, but evidently, somehow, whatever's going on in Jupiter doesn't affect me. Or I don't notice its effect. So the rules we want to make for multi-particle states, the kind of mathematical objects we want to use, need to kind of satisfy that, much in the same way that momentum didn't bother spin. I want whatever is on Jupiter to not bother me. And so we're going to use a tensor product structure again for that. So we're just going to recycle this. It's going to look the same. So if I say, there's stuff on the Earth, I'm going to call Earth stuff, I'm going to call collectively E, and Jupiter stuff, I collectively call J, whatever's going on in Jupiter. Then if I want to consider, and you could have sun and moon and Mars and Mercury, whatever, you can have the whole solar system. I'm going to work with the solar system without a sun, with just these two planets, all right? So if I want to have the Jupiter-Earth system, okay, and I want to just find a state psi, which lives, which describes stuff on the Earth and Jupiter, then I can express that, or at least a basis of states. I'm going to posit, I can think of it as something from Earth, tensor something from Jupiter. Okay, I'm going to posit that stuff, that separate degrees of freedom that don't in any way that we can tell interact, to get that non-interaction stuff, somehow that system, the combined system, must live in a tensor product space. And so I'm going to, just make that as a posit. Basically, you guess and check. You're going to guess that it's true, work out the consequences, see that it's right. And then interactions between what happens in Jupiter and the Earth are going to cause this to not cleanly separate, or it'll intertwine the information. But as long as they're separated, that's what I would expect. Okay? So, and again, I'm not going to write the tensor product. I'm just going to combine these to write this as one state, which is labels on Earth, comma, labels on Jupiter. Right, that's my tensor product space. Okay. All right. Is that okay? I'm trying to connect the example we did with neutron scattering off a crystal to these, because it's really the same math. There's the same linear algebra. So, very good. I want to go through and I want to write out some explicit states very carefully, very explicitly, because they're going to be the ones that get used in EPR and also Bell's theorem in particular. And so I want to write down and kind of not just random states, but really label them carefully. So we can define basis states. So let's imagine I have two particles, 1 and 2. I don't have to put them on Earth and Jupiter. They're just two particles. They can be in this room. Doesn't matter. And each one, it can be, they're spin half particles, so +1, -1. So the basis of states for the total system would be the following. Well, you could have plus or minus 1 for particle 1 in the z direction. A lot of labels. And you could have plus or minus z for particle 2. So what's the dimensionality of that? How many independent choices can you make? What do you think?
Should be 4.
4, yeah, well, or tensor products live in the, you multiply the dimensions, 2 dimensions times 2 dimensions, not 2 plus 2. If it's Cartesian products, you would add them. If it was tensor product, you multiply them. All right, so 4 is a tricky one because it could be the sum or the product. But it turns out, think of it as the product. All right, so these, okay, so, and man, that's awful, but that's what it would be, right? We can simplify the notation a little bit if we do the bookkeeping, and we're going to just choose to label one particle, we'll put the particle 1 stuff first, particle 2 stuff second, so I don't have to keep writing 1 and 2, 1 and 2, 1 and 2. So I'm just going to rewrite this. Okay, so I'm going to just write this as plus minus z, comma, plus minus z. I'm going to imply that this is for particle 1, or system 1, and this is system 2. And these are subsystems of the total system, which is the composite. Okay, and that's what I have. These are basis states for the 4-dimensional state. So I could have plus z plus z. I could have plus z minus z. I could have minus plus. And I could have minus minus. And those are fine states. And they're complete, which means any other state could be written in terms of those. So I could use those in my as my basis set. I could choose this to be my basis set, but I don't have to, and turns out I won't want to do a lot of the interesting things that people want to do in quantum mechanics. So instead of using these 4 states, I'm going to mix them up, take linear combinations of them to form new basis states. It's no different than saying, I think of this room as X, Y, Z, or I could turn it and think of it as X, Y, Z. It's just a linear combination. I'm going to choose a different linear combination, and I'm going to define the following states. A plus minus are 1 over root 2, and I'm going to say it's going to involve these middle two, the mixed combinations. So it's going to be plus z minus z plus or minus minus z plus z. Sorry for the board use spacings with that. So this plus or minus has to do with the minus sign in the superposition. The reason I used A as the label is it stands for anti-correlated.
Oh, and then so you just use C for correlated?
Yeah. It's because if system 1 produced plus Z, then you would know 100%. So that means that, so if you do a measurement of spin 1, 50-50, you get this or this. But if you get this, then it's guaranteed that the other one is going to be down on. They're anti-correlated. The two systems are You don't know, basically, you won't know whether you're gonna get plus or minus for spin 1, but whatever it is, you know that spin 2 is opposite, so they're anti-correlated. The correlated states are just, they're built out of the top and bottom ones here. So they're 1 over root 2, and you're gonna do plus z plus z plus or minus minus z minus z. Okay, and so again, you don't know whether if person 1 or system 1 is measured, you don't know if you're going to get plus or minus, but whatever you get, you know that if you make a measurement on the second system, you'll get the same. So they're correlated. Okay. Yeah. All right. The one that is most important for us in a lot of these experiments is going to be, or a lot of our thinking is going to be anti-correlated minus. That's going to be the big one for the EPR paradox. And anti-correlated with a minus sign. And it turns out that one it's called a singlet state. It doesn't rotate. So when it turns out it's invariant under rotations. It's like a scalar state. It has 0 angular momentum or 0 total spin, and so it doesn't. It's an s orbital or something. You can say lots of ways in different ways of thinking of it. I don't want to use the s orbital, but whatever. It doesn't rotate. It's a singlet. Is the vocab that people use. That's the one that gets used, or that you use a lot in these kind of mental proofs. In the notes, I kind of sketch that it's a singlet state. To really prove it, using what we have seen, you would have to go through. You have to take linear combinations there. It would be it would be an algebraic slog. In principle, we've done it all. That's one you'll have to do in class. In all honesty, I wouldn't expect that you could just see that that's true, but it is true. The other 3 go together. So these 2 and the other one go to form a triplet of 3. So thinking of a hydrogen atom, what's that analogous to? This one doesn't rotate, doesn't change when you rotate. It's a singlet. It's like an s orbital. The other 3 they would transform as a vector. Actually, it's analogous to a p orbital. Yeah. So, and because I only have 4-dimensional space, that exhausts all possibilities. You could build larger and larger things, and you could get analogs of S, P, D, F. Just more and more things. Yep. Okay. The other ones are not going to be relevant for us, but they are there. Okay. Emily, do you have any questions on that?
Don't think so.
Okay.
The only thing is just having trouble seeing where that comes from, but
Where it comes from?
like why where it comes from, really.
Yeah. So here's the thing. I mentioned, before I was recording things. Conservation laws, classical conservation laws, have are represented in the quantum structure as well. Probably logically the way to think of it is that there are quantum conservation laws which become classical. All right, but whatever. And one of them being angular momentum, So systems with rotational invariance conserve angular momentum, and so what happens is things like you have a system with no angular momentum, like in an s orbital. It's some sort of generalized picture, and then say it's unstable, splits into pieces. Well, the angular momentum has to be conserved. If it started with 0 total angular momentum before, when it splits, the individual pieces they will have momentum, but the total has to be conserved, which means that they have to be anti-correlated.
Okay, that makes
So that's really, in fact, that's very literally why we focus on this state. Right?
That makes sense.
Yeah. Yeah. Okay. So let me write that up here. Well, I'll rewrite it when I need it. Okay. Let me pause the video there and we'll do EPR next, because that way they don't get to be so long.